This week, we're going to be extending what we know about functions and their graphs. And basically, we're going to be looking at what happens when we make minor, and we'll talk about what this means more in class, but when we make small changes to a function, either in its input or its argument, so sort of directly to the x value, or to the output or to the function itself, so sort of outside what the function does, what those do to affect how the function behaves, how it works, what its graph looks like. So, sort of blanket term for all this is transformations. We're going to look at a bunch of different types of things that we'll talk about in a second here, but first, we're going to want a starting place. So sort of some common function types that we just sort of recognize. So what you should do now is pause the video for a minute, grab a graphing calculator, use an online one. Desmos is a good free online option that will generate some nice, clean looking graphs. And just go to an empty page in your notes, graph each of these things, just sketch the graph. Maybe make note of the domain and range, but sketch each of those real quick so that you have some idea what they look like, and then come back. Okay, I assume you're back now. We're going to look at an example of taking one of those function types. So this is the square root function. I've got it here in a dashed line just so that we kind of keep track of where the original thing is without any transformations or anything applied to it. Notice that the domain and range for the square root function are both 0 to infinity. 0 is included there, but does actually hit the point 0, 0, and then continues off to the right and up. So 0 to infinity with 0 included. Now, these, again, I said like minor changes that we're going to make. The first type that we can talk about would be if I add or subtract something either to the inside, so to the x value itself, or outside, which would be like changing the y value. So another way that you could write this thing, I've named the thing f, but what this would look like for this specific function would be something like that, right? So these a values are being added on the inside or underneath the square root directly to the x value. B, whatever it is, and they're both at 0 right now, so it doesn't change anything. B is being added outside of the square root. If you think about order of operations, that would happen after taking the square root. Right? Square root counts like an exponent, so it happens pretty early. But it also counts as though the stuff is grouped in parentheses. So for thinking order of operations, first thing that would happen there if I gave you, specific values for x and a and b would be that you'd add x and a together, then take the square root, then finally add b. Okay, so what we're going to look for is what happens here. So the graph in red is this, new sort of changed or transformed graph. And what I'm going to do is change the value of a, right? It's 0 right now, so we're not adding anything. B is not in the picture yet. So if I make a to be some positive value, so this is like the square root of x plus 5 underneath, you can see what the graph does. If I make a to be a negative value, you can see what the graph does. Hopefully you can tell that, as I slide this thing across, a is -3 right now, and the graph is now sitting at 3, 0, where before that kind of base starting point was at 0, 0. So if we wanted to kind of summarize what that's doing, we'll call this a shift. Some books and sources, you might see it called a translation also. It's taking the graph and basically just picking it up and moving it. But with this value that's being added to the inside directly to the x value, what's happening is that shift or that translation is happening only to the left and right. So it's shifting horizontally then. So a horizontal shift happens when we change something by adding or subtracting from the x value directly. Now, there's another interesting thing that you might notice here, and that's that when a is 5, so the inside part of that function is x plus 5. So I've increased the input, the x value, by 5 before the function does its thing. We actually shift to the left. And that might feel a little bit backwards. It feels a little bit backwards to me still, and done this many times, but that is how it works. So increasing that shifts everything to the left, decreasing shifts everything to the right. One way you can kind of think about this is that if we're adding to it, what we're doing is making everything happen earlier. So by increasing that x value, we're just like moving the timeline up a little bit. So if I think about my x-axis as being when things are happening, it shifts everything to the left, which is like everything's happening a little earlier. Okay, so that's horizontal shifts. Now this b value, which again is happening on the outside after the square root, there's me adding b, so square root of x plus 5. And what I see is that the graph is again shifted or translated, but now it's moving up. B is -5, so we're subtracting 5 now. Again, the graph shifts or translates, but now it's moving down. Again, how far it moves corresponds directly to what that value is. Subtracting 5 moves it down 5, adding 5 moves it up 5. So the vertical shift or the vertical translation is a little bit more straightforward because it does kind of exactly what it looks like it should do. If you write this out, I'll just do it right here. Sorry, I don't really have a way to write on this. The square root of x plus 5, what that does is take the square root of x, the square root function, and move everything up 5. Because it's as though it's taking the y values that were there and making them 5 bigger. Well, that slides the whole thing up 5. Okay, so that's vertical and horizontal shifts. Now, another way that we can change or modify the function would be by doing some kind of multiplication. That could be changing a sign, either on the inside or the outside. This first one, I'm taking the opposite. It's happening on the outside of the function, so I'm multiplying by a negative sort of out in front of the whole thing. That's what that looks like. The second, I'm changing the sign, multiplying by negative on the inside. If it will let me click on the thing. Sorry, I'm going to move that out of the way. Okay, there we go. All right, now these are called reflections because what they do is take the function and preserve the shape, but change the orientation by essentially holding something still and reflecting it, like mirroring it. So what's happening here is that the x-axis stays put, but what that negative does is take all of the y values and force them to be the opposite in sign. So if they were positive before, now they're negative, or vice versa. What that does is reflect over the x-axis. So negative out in front or on the outside of the whole thing is an x-axis reflection that's going to flip the graph upside down. On the other hand, if I put a negative on the variable itself, on the inside of the function, before, whatever the function action is happens, then what happens is we get the opposite value for all of the x, all the input values. If it was positive before, now it's negative, vice versa. So what happens is that we reflect, but the thing that stays still is where x is 0, which is the y-axis. So the y-axis stays put. The graph reflects, so it's kind of backwards. It's like swapped left for right now. And we get what we call a y-axis reflection. Okay, the other possibility is if we multiply by some value, that's called scaling. What that's going to do is kind of modify the shape of the graph a little bit. And I'm just realizing I didn't build this in here to begin with. There we go. Okay. So I'm multiplying. Notice it's on the outside. It's before the function does its thing, c times f of x. So again, with this square root function, that's like if I had a 2 sitting out in front of the square root or something. C is 1 right now, so it's not changing anything. What that's going to do is scale the function, and what scaling does is stretch it out or shrink it down. So, I'll let you kind of conjecture and figure out how these values work. There's back to c equals 1, so that's our parent function, right? That's kind of resting like natural state. If c is bigger than that, watch what happens as the value of c increases. If c is smaller than 1, then you can see there what happens. Now, I'm being careful not to let c go into the negatives, because what's going to happen then is that it would reflect also. So I'm trying to avoid that. But if c is smaller than 1, like imagine, trying to stay on the half. Okay, whatever. Pretend it's a half, whatever. What you're doing is taking all of the function values or the y values or the height of the function and cutting those in half. So the whole thing looks shorter. So we call that shrinking sometimes, or I like to think of it as a compression. So it's like you grab the graph by the top and the bottom and just sort of squish the whole thing down, right? Like if it was on Silly Putty or something like that, squish the whole thing down. The shape of the graph is the same, basically. It's just shorter. It takes longer to do the same sort of thing. On the other hand, if I take the whole thing and multiply it by 5 or something, it still does basically the same thing. It goes to the same places. It hasn't really like moved where it sits, but it's taller. It's stretched out vertically. So that should give us a good starting point for talking about things in class. I will send you a copy of this Desmos graph, so you can kind of play with it a little bit yourself and sort of fiddle with these sliders, and hopefully that'll give you a better sense of what's going on. Okay, great. I will see you in class.